Hi, everyone. I am Yiren Zhang from Shanghai AI Lab. I am here to present our newly proposed network architecture for efficient sequence modeling called Toeplitz neural network. Before introducing our network, let us briefly review some efficient sequence modeling strategies for large language models. The first one is sparse transformer. It improves the modeling efficiency by sparsify attention matrices as shown on the right. Note that the performance of sparse transformer is upper bounded by vanilla transformer. Linear transformer is popular mainstream strategy for efficient sequence modeling. It improves the efficiency by switch the multiply order of QKV in attention operation. It assumes the sequence length is greatly larger than the feature dimension. However, this assumption may not hold in large language models. Long convolution is a new trend in efficient sequence modeling. RTNN belongs to this strategy. Instead of computing the softmax attention, the long convolution uses a specifically designed matrix to replace the attention matrix. Since it does not require the n greatly larger than d assumption, and its performance is not bounded by vanilla transformer, long convolution becomes one of the promising strategy to replace transformer in large language models. RTNN is closely related to two concepts: relative positional encoding and Toeplitz matrix. An attention with relative positional encoding can be written as the equation here. The relative information is added to attention as a bias. A Toeplitz matrix is a special form of a matrix that has constant values along each diagonal running from left to right. There are two nice properties of a Toeplitz matrix. 1. It only contains two n-1 parameters for a n times n matrix. Second, the computation complexity of Toeplitz matrix vector production is O(n) log n. Here we show how to representing relative positional information with Toeplitz matrix. Recall the expression of attention with relative positional encoding. It can be rewritten in a matrix form as shown here, where the W is actually a Toeplitz matrix with TIJ equal to Wi minus J. In transformer-like structure, there are two main operations. One is token mixing and the other is channel mixing. The token mixing often refers to the attention operation X, where A is the attention matrix and X is the token matrix. Channel mixing is the FFN operation after attention operation. In TNN, we mainly change the attention operation to Toeplitz matrix operation. In short, we discard the QK multiplication in attention operation while only keeping the relative positional matrix. Surprisingly, the model still works well in such simplified version. The overall architecture is shown below. We use GTU to perform token mixing and GLU to do the channel mixing. We use a small MLP to generate relative positional coefficients and fill them to Toeplitz matrices. Input length extrapolation ability recently attract attentions as it allows a model to infer a longer sequence than that in training while maintaining its performance. In TNN, such ability can be easily achieved by applying an exponential decay bias to the Toeplitz matrix. As shown on the right, all models are trained with a sequence length of 512. As the inference sequence grows, the TNN maintains its performance. We perform language modeling and bidirectional language modeling in Wikitext 103 and GLU benchmark. Our method achieves better performance than vanilla transformer. In long-range arena benchmark, TNN achieves the best performance than all other competitors with a clear margin and faster than most of them. We also provide a detailed speed comparison in long-range arena benchmark. TNN is more than 5 times faster than vanilla transformer when the sequence length is 2K. We also implement TNN in image modeling. As shown, TNN achieves better image classification results than transformer in ImageNet benchmark. For the ablations, please refer to the paper for more details. Thanks. Please scan the QR code for our TNN implementation.